Good morning. Today I am going to deal with two more oxidizing agents. One is HIO4, another one is lead tetraacetate. The important application of these two oxidizing agents are cleavage of 1,2-diols into carbonyl compounds. Let us discuss with the first one, that is HIO4. This is the structure of HIO4 and it is existed in the form of hydrates, that is HIO4.2H2O. This is the structure of HIO4.2H2O, and it is also exist in the form of its salt like NaIO4, KIO4, etc. Then come to the first important application of HIO4, that is cleavage of 1,2-diols into carbonyl compounds. This is the reaction. Here 1,2-diol. This is a glycol which in the presence of HIO4 it will convert it into carbonyl compounds. Then what is the mechanism of cleavage of 1,2-diols using HIO4? Here in the first step it eliminates 2 moles of water and it will convert it into this structure. Again 1 mole of water molecule getting eliminated and it will convert it into double bond O. Then it will undergo CC bond cleavage and it will convert it into RCHO plus RCHO plus IO3 minus. What is the stereochemical aspects in the case of oxidation of HIO4? Syn-1,2-diols readily participated in HIO4 oxidation than trans. Here, this diol will react faster than this diol with the HIO4. Another application of HIO4 oxidation is oxidation of alpha ketol to carbonyl compound and carboxylic acid. This is our alpha ketol. Alpha position is hydroxyl group. Then when it is treated with HIO4, it will cleaved into CC bond and it will convert it into aldehyde and this part will convert it into carboxylic acid. Another application is oxidation of alpha amino alcohol to carbonyl compound and ammonia. This is our alpha amino alcohol. When it is treated with HIO4, it will convert it into RCHO plus R-CHO plus NH3. Another application is oxidation of 1,2-dicarbonyl compounds into carboxylic acid. This is 1,2-dicarbonyl compounds. When it is treated with HIO4, it will convert it into 2 moles of carboxylic acids. For example, this is a compound having 1,2-diols. When it is treated with HIO4, the first part, that is 1,2-diol, it will convert it into CHO and this bond will break and this bond will convert it into CHO, CH2OH. Again, that is a alpha hydroxy ketone. When it is treated with HIO4, it will convert it into HCOH and CH2 double bond O. So in short, what are the products of this oxidation using HIO4? 2 moles of HCOH CHO and 1 mole of carboxylic acid, that is our formic acid. That is, this is our primary alcohol, this is our secondary alcohol. Primary alcohol on oxidation with HIO4 will give ketones, whereas secondary alcohol on oxidation will give carboxylic acids. Then what is the case of this compound? When it is treated with the 3 moles of HIO4, it will cleave this 3 CC bond, and the first compound is a primary alcohol, which will convert it into aldehyde. Secondary alcohol and secondary alcohol both are will converted into carboxylic acids. Then last one is again primary alcohol, so it will convert it into our aldehyde. Then what is the case of this compound? Here this is our primary alcohol, then there is a carbonyl compound. So first it will cleave this bond and convert it into HCHO and carbon dioxide. Then followed by this cleavage, it will convert it into HCHO. Another important application of HIO4 is to distinguish between pentose and hexose. We know that pentose having 5 carbon atoms, whereas hexose having 6 carbon atoms. This is a pentose, CHO, CHOH, thrice CH2OH, which on treating with HIO4. What are the products? We get first group is CHO, and all the other 3 groups are secondary alcohols. So all these functional groups will converted into carboxylic acid, and the last one is our primary alcohol, it will converted into aldehyde, HCHO. So we get 4 moles of formic acid and 1 mole of formaldehyde, which means it can consume 4 moles of sodium bicarbonate, whereas in this case this is a hexose. Here we get 6 moles of carboxylic acid, 5 moles of formic acid and 1 mole of formaldehyde. So from this number, or from the moles of sodium bicarbonate used with this carboxylic acids, we can predict the structure of, or we can predict the number of carbon atoms present in the carbohydrates. Why it is widely used in carbohydrate chemistry? Because HIO4 is readily soluble in water. Therefore, HIO4 oxidation widely used for the structural elucidation of carbohydrates, since carbohydrates are soluble in water. Another application of HIO4 in the field of carbohydrates are to determine the ring size of carbohydrates. Here, when this alcohol attack on this carbonyl compound, there is an intramolecular reaction of alcohol and aldehyde present in the carbohydrates. It will convert it into a cyclic compound. When this cyclic compound reacts with the methanol in the presence of acid, this OH group getting protected and it will convert it into OMe. When this cyclic compound undergoes oxidation using HI04, this bond and this bond will cleave and what will be the product? This is our secondary alcohol. It will convert it into CHO. Then this CHOH bond will breaks and it will convert it into HCOH formic acid and this alcohol will oxidize into carbonyl compound. Then what will be the structure of the product? This is the structure of the product plus we get 1 mole of formic acid. So the ring here the ring size is 6, whereas if this oxygen lone pair of electrons present in this OH group will attacks on this carbonyl carbon, the ring will be size of the ring will be reduced. Then when such a ring will undergoes oxidation with HiO4, there will be no carboxylic acids as a product. So from this reaction we can determine the size of the ring. If the ring size is 6 in the case of carbohydrates, we get 1 mole of formic acid, whereas if the ring size is 5, we get no carboxylic acids as products. Another oxidizing agent is lead tetraacetate, or it is called LTA. This is the structure of lead tetraacetate. What are the important application of LTA? First one is cleavage of 1,2-diols into carbonyl compounds. Same as HiO4, it will cleave CC bond and it will convert it into this product by the elimination of 2 moles of acetic acid and we get this product. In the next step, it will undergo CC bond cleavage and converted into carbonyl compounds. Here 2 moles of carbonyl compounds and LTA will convert it into lead acetate. Then what about the stereochemistry of LTA oxidation? Same as HiO4 oxidation, it also prefers syn diols than anti. Since diols reacts faster with LTA than anti 1,2 diols. Another application is oxidation of simple alcohols into aldehydes or carbonyl compounds. Here, this is our primary alcohol. Primary alcohol reacts with LTA to form aldehyde, whereas this is secondary alcohol. It will oxidize into carbonyl compound. And LTA do not affect multiple bonds. Here this is double bond and this is OH function. When it is treated with LTA, double bond will remain unchanged and CH2OH primary alcohol getting oxidized into aldehyde. Another application of LTA is oxidation of 1,2-dicarbonyl compounds. 1,2-dicarbonyl compounds converted into carboxylic acids by the cleavage of CC bond. Another application is reaction with carboxylic acids. That is, or it is also called oxidative decarboxylation. First one reaction with the monocarboxylic acids. In the presence of LTA and copper salts, it will convert it into alkenes by the elimination of carbon dioxide and hydrogen. And in the case of dicarboxylic acids, LTA reacts with the dicarboxylic acids and it will again convert it into alkenes by the elimination of 2 moles of carbon dioxide and 1 moles of hydrogen. Then this is another carboxylic acid, that is gem carboxylic acids. What do you mean by gem? Two functional groups attached with the same carbon atom. This gem. This is a gem carboxylic acid. In the presence of LTA, first it will acylated, then followed by hydrolysis, it will converted into gem diols. Then easily gem diols will converted into ketones. So the final product of gem diols on LTA oxidation is ketones. Then another reaction of LTA is with alpha keto carboxylic acids. Here it will breaks the CC bond and it will convert it into RCOH plus carbon dioxide. Another application of LTA is it can act as methylating agent and acetoxylating agent. When LTA used, it introduce methyl or acetoxyl group at allylic position or benzylic position or alpha position of electron withdrawing group. Here is an example. This is an allylic position. When it is oxidized with LTA, we get two different products. One is methylating product, another one is acetoxylating product. And again, this is an allylic position. We get two different products on LTA oxidation. One is here LTA act as a methylating agent and here LTA act as an acetoxylating agent. Then if we use BF3, we get more acetoxyl products. So here this is an electron withdrawing group and this is its alpha position. On treating with LTA, it will convert it into acetoxyl products. Then what is the reaction of LTA with the naphthalene? Here naphthalene getting acetoxylated. In the acetoxyl position will substitute in this position. That is our alpha position of naphthalene. That's all about HI04 and LTA. Hope it is clear. Thank you.